Let's start this chapter with a relatively intuitive and simple example. Let's say that you have a cell over here, or any structure, well, a circle. Okay, let's talk about a circle. And you're drawing this circle with a diameter of, let's say, 1 centimeter in your notebook. And next to it, you draw a slightly larger circle, sloppily drawn, unfortunately, and now this one has a diameter of 2 centimeters. And the question is now, how many times larger is cell B, circle B, compared to circle A, shape A and shape B? Now you're gonna say intuitively, probably, well, it's 2 times larger because the diameter is twice compared to cell A, and you're correct. However, you could also say, well, actually the area is 4 times as large as the area of shape A. But when we're dealing with magnification calculations, we're not talking about area. We're also not talking about volume. All we really care about is so-called linear magnification. So we only look at the diameter of two-dimensional pictures. Everything else is not relevant, because, do not forget, a cell is a three-dimensional structure and it does have a volume, and a cell that has twice the diameter actually has 8 times its volume. So the mass is 8 times larger if you only increase the diameter 2 times. But we're not gonna worry about that. All we care about diameters and distances, and not about area and not about volume. That's why we talk about linear magnification. So let's move on to the next slide. What is the formula for magnification? It is the size of the image divided by the size of the specimen. And when you said that the magnification is 2 times, it's 2 times larger, what you in reality have done is you have divided these two values. The size of the second image was 2 centimeters across, and you divided it by the original, which is was 1 centimeter across. If you divide these two, then you get a magnification of 2 times. The units cancel, and that's what you have done. But a magnification of 2 times is really a very small value. So when dealing with microscopic images, microscopic image is actually a wrong term to use, because the image itself is not microscopic. That's why you refer to them as micrographs. Micrographs have a magnification which is of course much larger than 2 or 3 or even 10. So let's have a look at it's overlaps, so let's do it like this. The size of the image is usually expressed in centimeters. Of course, because you use a ruler to measure it out. Of course, you can also use millimeters if you want to, but centimeters is also fine. But if you use millimeter, then you have to know that 1 millimeter is 10 to the power of -3 meters. That is 1 millimeter. So you might as well note this down. It's also quite useful. And the size of a specimen, because we're talking about cells, is usually expressed in micrometers. And 1 micrometer is 10 to the -6th meter, or 10 to the -6th meter. And you see that this micro sign is a U with this extended arm down here. Okay, that's the sign for micro. So micrometer is written like that. So let's start right away with an example. The drawing of a cell is 6 centimeters across, and the original size of the cell is 10 micrometers. What is the magnification? So we write down the following. Magnification is the size of the image, which is 6 centimeters, divided by the size of the specimen, which is the 10 micrometers. And we divide it out. But can we really do that? No, we cannot, because centi and micrometers are different units. So we have to convert everything to the same unit. And what I would like to recommend is that you convert the centi to the 10 to the negative 2. So 6 times 10 to the negative 2 meters divided by 10 times 10 to the negative 6. Remember this one over here, meters. And now we can simplify this formula. And the first thing that we can do is we can cancel the meters. Now that might be a little bit unusual, you might think, because you're in math class you learned that you can cancel variables, but you can also cancel units. And so these meters cancel, and we have 6 times 10 to the negative 2 divided by 10 times 10 to the negative 6. And we now have to somehow remove this 10 to the negative 6 down here. And what we do is we simply switch the sides and reverse the sign. So 6 times 10 to the negative 2nd over here plus 6. And now we got this across, but we still have the 10 over here divided by 10. We continue to simplify. 6 times 10 to the negative 2 plus 6 makes to the 4th. Always write nicely, the x is not nice. Divided by 10. And now this should be a 4, it looks like a 9. So can we simplify this still further? Yes, this is the same as 6 times 10 to the 3rd is the same as 6,000 times. And that is your answer. So the magnification is 6,000. I know some people like to write an x over here to indicate the times sign, but you could confuse this with a variable. So that was basically example number 1. And the purpose of this example was not only to show you how to stick in these values into the equation here at the top, but also to show you a little bit how you can simplify fractions that use exponents. Because something I would not recommend is if you start writing out these values over here in terms of 0.006 and 10 times 0.000 whatever. No, don't do that. You're going to miscount the zeros. I would actually say it's much better if you use this type of notation using the exponents. Okay, there will be more examples in different videos, but it will not get sufficiently more complex than what I've shown you over here in this example.